Hello everyone, so today I'm going to start a new section of the math series. It's called optimal control, and I'm going to introduce you a prologue. It's the Brachistochrone questions, and for somebody who are familiar with that, this is the Brachistochrone question. It's essentially the question that Bernoulli asked the whole Europe, and then Newton solved it in one night. I think that's a famous story. And now we are going to solve it today. So the description of this question is fairly simple. It says we start from a point which is from h, 0h. It's a point right here. And then we want to go to here, which is L0, right? And we have several ways to go from one point to another point. Suppose we want to do the shortest distance is this straight line, right? Or because here is a gravity. Or we can let it go straight down to here 0, 0. And then we go this way. There are two ways, right? But in both ways, not the Brachistochrone, which means Brachisto means a short, and chrome means a time. But in both ways, not the shortest time. So actually, I can give you a little bit of spoiler. It's this one. It's red 9. This one. It is the answer, and then it's called a cycloid. And in Chinese, it's called 百线. Alright, so today I'm going to prove this. And to solve this question that Newton solved for a night, we need to know a technique called the calculus of variations. So what is calculus of variations? It's essentially one step above the calculus. Let's take an example. Oops. Suppose we have a calculus question is like this. I have a function and I want to find the maximum. That's a calculus question. I want to find the maximum. This is calculus. But if we want to solve the calculus of variation questions, it's just one step further. So suppose we have an integral I of a function y, and this is equal to the integral from x1 to x2 of this yx dx. Then I want to find a function y such that Iy is maximum or minimum. Then this is what we call a calculus of variation questions. So we want to, instead of find a value, this time I want to find a function. That's kind of the story. And in order to solve this, so what should we do? Let's show you by these Brachistochrone questions. We know this Brachistochrone question is we want to do the integral from 0 to L dt. Minimize, right? This is a capital T. And where this dt is actually the distance divided by speed. So here is equal to the distance divided by speed, right? For every moment. And we want to minimize this. We want to minimize this t. And then what should we do? Firstly, let's express this ds and v as a function of x and y. First, what is ds? We know by the Pythagorean theorem. We know it's equal to dx squared plus dy squared, take a square root. That's Pythagorean theorem. Maybe Pythagorean. Maybe some typo. It's Pythagorean. It looks like this. And then what is v, x, and y? For this one, we should use physics, right? Use physics. We know by the conservation of the law, I think it's called conservation of energy. Let me check. Conservation of energy, sorry. Conservation of energy law. Of energy law. What do we get? We know the energy at place H is equal to the energy at place Y. But now we have another part, which is the kinetic energy, right? So this is potential energy. So it's potential energy. Here is equal to another potential energy plus kinetic energy. And based on that, we can write a function v out. Now the function v is equal to what? It's a function of h and y. And it turns out n can be cancelled. So v is equal to square root of 2g times h minus y. That's our function. And now we have the function t is equal to what? It's equal to integral x1 to x2 of this dt, which is equal to square root of dx square plus dy square divided by this 2g h minus y. And we don't want dy and dx, and it's all over here, so we can rewrite it as an integral of x1, x2. We divide it by dx, both sides. So what do we get? We got the square root of 2g h minus y. Here is just square root of 1 plus y prime square, right? Because it's dy dx. Then we take a dx out. Now it looks like an integral over x, because now y is a function of x again. And I want to find a y such that t is minimized. I want to find a function to make this integral minimized. What should I do? The next thing is a famous equation. It's called the Cauchy. Euler-Lagrange, sorry, no Cauchy here. It's called the Euler-Lagrange equation. And we will derive it now. Maybe another video. Euler-Lagrange equation essentially says this. It tells you that when I want to minimize a function, so now let's make it more abstract. I minimize a function, I is this t, okay? It's equal integral of x1 to x2 of this function x, y, and y prime dx. There should be some property that y must satisfy. So it's a necessary condition. Then let's see what is that condition. Let's suppose we want to minimize this I, and suppose yx satisfy this we want to, and suppose yx satisfy this, then what do we get? Then we first know that yx1 should equal to y1. yx2 is equal to y2 because of this. Because now I have a function, make it more generous, from x1, y1, here is x2, y2. This is the boundary condition. Then boundary condition must satisfy. And then what do we get? We have the boundary conditions. Then let's suppose we have a function eta x. And for this function, we only need eta x1 equal to eta x2 equal to 0. Maybe this eta is ugly. Maybe eta x2 equal to 0. And there's no other restrictions. So no other restrictions. Under these circumstances, let's define a function y bar x is equal to yx plus epsilon times this epsilon x. Then it's a family of curves, right? And for this family of curves, what do we know? What do we know is this I of this epsilon is equal to the integral x1 to x2 of this function x, y, y bar y bar prime dx. And it's a function of epsilon because x get integrated out. So it's only a function of epsilon. And since we want to know what is the minimum of this I, we need some property to be satisfied. The first property is that di epsilon is equal to 0. So I will reach the stationary point. It's a stationary point. It's not a necessary maximum minimum. It's maximum minimum. Right? It's a stationary point. But we also know that actually when epsilon equals to 0, this is equal to 0 because it's essential to say that yx is the desired function. Now with this equation, let's see what is the Euler-Lagrange equation. Since di epsilon is equal to 0, let's write it down to see what will happen. Because we know I is equal to integral x1 to x2 f x y bar dx. And we can take the derivative inside the integral. So put derivative inside integral. And here, of course, we will assume the regularity will satisfy. I mean the DCT or MCT, such things, because we change the order of derivative and integral. Then di epsilon is equal to integral of x, y, x2 df d epsilon dx. Makes sense, right? Or I'll change your notation. Maybe we take the partial derivative. Looks easier. And the next step is we want to see what kind of properties will this equation hold. So firstly, this df d epsilon is equal to what? Check. We should use the chain rule, right? Let's use the chain rule. Actually, here is the total derivative, so it's a d. D means the total derivative. And here this D means the partial derivative. Maybe this makes the notation more clear. So by the chain rule, what do we get? We know x, there's nothing with respect to epsilon, so we only need to deal with the y first. dy times dy as the first part. The second part is df dy prime times dy prime d epsilon. And then integral with respect to x, of course, again. But again, we know y bar is equal to yx plus epsilon times eta x. So y bar prime is equal to y prime plus epsilon times eta prime. So in this case is dy bar the epsilon is equal to eta x, dy bar prime the epsilon is equal to epsilon prime x. And we will put this into our equation. We will get integral from x1 to x2 times df dy bar times dy the epsilon is eta x plus df dy prime times this is epsilon prime x dx. And we can simplify a little bit more. Let's deal with this second part. Let's deal with this part. What is df dy prime times y prime x? Here we can use the integration by part. I take this whole thing out. So integral, let's change back to white. It's integral x1, x2 of this df dy prime times this dx. We can consider as integral of u times v prime dx. We can, of course, right? Which is equal to u times v, which is equal to u times v minus integral of v u prime dx. Right? So we write this as correspond to the real function, which is equal to df dy prime times v is just integral of this thing, so it's eta minus integral of vu prime x, v is eta times the u prime is derivative of this df dy prime, right? But then we evaluate this function at x1, x2. We know eta evaluated at x1, x2 is all both equal to 0. So this term will go to 0. And what's left is the integral x1, x2 of this eta x times this derivative. And we'll put this thing back to our original I. So I is equal to integral x1 to x2. The first term is times eta. Here's a minus sign. Don't forget. Here's a minus sign. So minus eta times d dx and we know that I at 0 is when the y bar is equal to y, right? So let me write it more specifically. So when epsilon equal to 0, y bar is equal to y, I reaches minimum, in which I mean I0 is equal to integral x1 to x2 of this partial f partial y, there's no bar, times eta minus eta times d dx df dy prime dx. And for this function, we know since let me write one more step. We can factor this eta out, integral x1 x2 times eta out minus notation is not good. Just partial. Partial f partial y prime dx. But since eta is arbitrary, let me go back a little bit because I made some mistake. Here's di d epsilon, so here again it should be di d epsilon. And since eta is arbitrary, we must have is equal to 0 d1 dy minus d dx of df dy prime is equal to 0. And this is what we call the Euler-Lagrange equation. And I will show you how to solve the Brachistochrone question. Okay, now we continue the second part of the Brachistochrone problems. Now we have the Euler-Lagrange equations. Actually, we can solve it directly. But let me introduce something more, because we know that t is equal to the integral from x1 to x2 of this f x y bar, not y bar, y prime dx. But here, the function y, f, let me write it again, is equal to x1, x2. It's square root of 1 plus y prime square, here's square root of 2gh minus y dx. What I want to say here? I want to say this f is independent of x. Here, I don't mean it's independent of x, but it's actually, I think it does not contain x directly. So, because y is a function of x, so f does not contain x directly. So essentially, f is a function of y and y prime. Of course, y and y prime is a function of x, but f itself is not a function of x. And under these circumstances, we can use the Beltrami identity, which will make our life easier, because Beltrami identity will cover the special cases when f is only a function of y and y prime. So what is that? Let's go back to Euler-Lagrange equation. So Euler-Lagrange equation. Euler-Lagrange equation essentially says df dy minus d dx of df dy prime equal to 0. So if we times y prime both sides, the result will still hold, right? So essentially we get y prime times df dy minus y prime times d dx times df dy prime is still 0. And we will call this equation number 1. And with this equation number 1, the next thing is that we want to do some other tricks to these equations. So what is the total derivative of x, i.e. df dx? What does that equal to? Let me write that down. This is equal to the partial derivative of each component, right? It's a partial f partial x plus partial f partial y times partial y partial x plus partial f partial y prime times partial y prime times partial x. But since x does not occur, so x is not here directly, we know this term must be 0. That's the key, because we only have that next two terms. And let's simplify the notation, which I mean is df dx is equal to df dy times y prime plus df dy prime times y double prime. That's the idea. But here, let's see this term. This term occurs in equation 1, right? Let me go back to equation 1. Equation 1 is the Euler-Lagrange equation with times y there. So this is the exact same term. And now, actually, this term is equal to the second term, right? Because it's right sign 0. So we will substitute this box with this equal to equation 1. What do we have? So df dx is equal to, let's copy it, is y prime times the d, okay? Is equal to y prime times d dx df dy prime. And second term does not change, we plus again. But here, you see, luckily, these two terms, we can combine it with one term because it's product rule. So it's product rule. This is essentially d dx of y prime times f. You can check it by yourself. It's just product rule. So here y double prime times it, and here's y prime times d dx. Then we can move this whole term, to the left hand side, right? So it's just d dx of this f minus y prime times equals 0, right? Because it's equal to 0. And then we integrate it. We get f minus y prime times, and this is what we call the Beltrami identity. Okay, finally, we get back to the Brachistochrone question. We see Brachistochrone question is t is equal to integral x1 to x2 of this 1 plus y prime square. Is this question? And now we have the f, which is square root of 1 plus y prime square square root 2g times h minus y minus y prime times df dy. What do you get? Is equal to y dy prime is a half. That times 1 plus y prime square a half times a half here times 2 times y bar, and this is equal to some c. Let's simplify it. I can times the 2g to the right hand side, and we can times 1 minus, so that's times square root 2g h minus y, and we times square root 1 plus y squared both sides. What do we get? The first term becomes 1 plus y prime squared, right? Because we times this square root to it. The second term is minus y prime squared, a half and half times what? Right hand side is equal to c times square root 2g h minus y times square root 1 plus y prime squared. Here's 1 plus y prime squared minus y prime squared, so it's 1 equal to c times square root h minus y, because it's equal to another c1 maybe, times square root 1 plus excess, right? And the next thing is, let's solve it. This is a separable equation actually. I mean, we can separate y and x. And then after some derivations, we will see this is equal to dx is equal to square root of h minus y c1 times h minus y times dy. Then do the trig substitution. We let y equal to h minus c1 times sine square theta over 2. And we can solve for it. We will see that x is equal to and this is the parametric equation of the cycloid. So it turns out the Brachistochrone question, the answer should be the cycloid. Because maybe a little bit more explanation of that differential equation. So why want to solve this? Why this is separable? Let's see it. So let's times it out directly first. This is equal to h minus y plus h minus y times y prime squared equal to c1. Then we can move all the terms of y prime left hand side and all the other terms right hand side. So it's h minus y times y prime squared equals to c1 minus h minus y. And then y prime squared is equal to y prime is equal to square root of c1 minus h minus y, h minus y. And here we know y prime is equal to dy dx. So it turns out it's separable, right? Because we know it is equal to dx is equal to move dx to the right hand side and divided this fraction to the left hand side. So it's 1 over this. That's it. So it's separable. Then this is the thing